Sorry, recording myself is new to me. So first chapter is basic chemistry. So before each chapter, I'm going to have these learning objectives. So now you'll know what to focus on as we go through the chapter. So these are the things that by the end of the chapter, I hope that you'll be able to do. So we're going to start with predicting atomic stability from the subatomic structure. So we're going to learn that because if we're interested in biology, we have to know what's going to be happening on the chemistry level, and that's going to happen in a way that's going to increase stability of individual atoms. So we're going to have a lot of reactions and bonding between different atoms that's going to tell us something about what's going to happen with the biology. We're going to go over why bonding makes things more stable and why certain bonds happen. So this will give you some intuition as to how things are going to be working. We're going to be able to differentiate between two different kinds of bonds that we'll learn about, and we're going to learn how to predict how some of these bonds work as a function of their atomic structure. So by the end of the chapter, we'll go over this again, and hopefully those terms will make a lot more sense to you if they're new to you now. So why do we care about chemistry? Sort of like I mentioned before, the chemical structure of different atoms and molecules is going to dictate the larger biological function. So everything in biology really comes back down to the chemistry. And so if we have some intuition of how the chemistry works and what things are likely to happen in different scenarios, it's going to help us kind of guess what's going to happen with the biology. So we're going to focus a lot throughout the course on how structure informs function. So the structure of everything in biology is kind of carefully maintained to produce a certain function of different parts of the cell or different cells or different parts of your body. All of those functions kind of are derived from the smaller structure. And so if we can start to understand this a little bit better, it's going to give us a good intuition for what we're going to see biologically. So here's an example. So if we look at cells are surrounded by these membranes that are kind of like their walls that allow them to keep an interesting an environment inside of the cell that gives them interesting properties and allows them to do really useful things. But it's important that they have a well-maintained boundary between the inside and the outside of the cell. And so the way that happens is the cell makes a lot of these molecules that we'll go over in the next few chapters called phospholipids. And these phospholipids like to line up so they have their head, this red circle there, facing outwards towards water, and their tails inward away from water. And so when you have enough of these in water, which is what cells are usually in, they form these bilayers like this, so they can keep their tails away from the water and their heads out towards the water. And if you have enough of these, they're going to create a barrier between the inside and the outside. So what you make inside doesn't always just float away and go back outside, and so it allows them to control the inside of the cell. And so if we learn why some things like to face water and why some things like to not face water, we can learn how this works and what some of the properties are. And so we're going to be going over the groundwork of those ideas so that as we move forward, we have a better foundation. All right, here's our outline for today. I try to keep the slides pretty organized so you can use them to study and find information easier. I'll do my best to make sure I always have the learning objectives and the outline here, and then all the slides stick to it. But I'm going to make a lot of mistakes, so just let me know when I do, and I'll do my best to fix it. Okay. So when we talk about chemistry, especially the chemistry that has to do with biology, we're interested in like a really small subset of kind of larger chemistry. So when we talk about chemistry, there's a lot of elements. So if we look at the periodic table, which I'm sure you've seen hanging in classrooms before, that's a list of like all the known elements in the universe. And so there's a lot of those that we never really interact with in biology. So most of biology, so 95% of kind of organic biomass, like animals and plants and things like that, is made up of just 6 elements. And then there's 5 more that we find in like trace quantities. But other than that, that's really all we're going to be talking about. So Carbon, we're going to hear a lot. Oxygen, obviously, that's very important. I'm sure we're all aware of that. And then we have a lot of these other, minerals, things that we need to ingest to stay alive, but they're not found in very large quantities. So we're going to be talking about elements. So all the elements on the periodic table and all the ones that we're talking about, those are what we're going to think about as the smallest building block, like the smallest level of things that we'll be breaking apart. Any smaller than that, and biological systems don't really kind of break those things apart. Even though if we talk about physics and chemistry in those classes, we'll learn what's going on a smaller scale. So atoms. Atoms are individual species of a certain element. So carbon is an element. It's like a class of atoms. It's like the color red. It's like a descriptor of what an atom, what kind of group it belongs to. And then atom is the fundamental unit of that element. So we could have 5 atoms of carbon, but we're not going to have like half an atom of carbon. So it's like the smallest fundamental unit in that sense. So one way to think about it, atoms to elements are like the way animals are to species. So you could have, like a type of dog, and then you have an individual dog, just like you have a type of, element, and you have individual atoms within that. Does that make sense to you? All right, great. So within an atom, even though we said those are the smallest building block, there's parts that we need to know about that are going to tell us how that atom is going to behave. So we have 3 parts that we're really going to be talking about: protons, neutrons, and electrons. So these are all different in the charge that they have and where we usually find them on the atom. So in the center of the atom, we have the proton and the neutron. So the proton is positively charged, and the neutron, it has no charge at all. It's like a 0. And then surrounding the nucleus, where we find the proton and the neutron, we have the electrons, and those are negatively charged, and they just orbit around the atom. So atoms don't really share their protons or their neutrons usually, but they will share their electrons because they're kind of on the outside and they're not held as tightly. And when they share those electrons, it's going to tell us a lot about how they're going to be behaving. So 3 main parts: proton, pro, positive; neutron, sounds like neutral, like 0. Wow, this is elections. It's not supposed to be electrons, it's supposed to be electrons. Sorry. Yeah, no, elections luckily are not part of this course, so I don't have to talk about that. Electrons are negatively charged, and they're going to be on the outside of the atom. So when we're talking about atoms, we're going to use 2 different terms, and these are going to help you know what atom we're talking about and how it's behaving at the moment, sort of. So atomic mass, so that's going to tell us the number of protons and neutrons. So since electrons orbit around the outside of the atom, and those really don't have a noticeable mass. Those are much, much lower mass than protons and neutrons are. So the atomic mass, or like the total mass of that atom, is really going to be a product of the number of protons and neutrons. So atomic mass is really like the mass of that atom, and electrons are small, and they're kind of hovering around, and we don't really take them into account when we talk about the mass. Protons and neutrons have a much higher mass, and so that's why when we talk about atomic mass, we talk about those 2 particles. Atomic number, that's going to be the number of protons. So if we look at the atomic number and the atomic mass, we can figure out how many neutrons there are in the atom as well, just from doing the math of those 2 numbers. So that's going to tell us some information about what's going on with that atom. So usually we're going to assume that atoms are neutrally charged. So our atomic number, we can assume, is the number of electrons we also have. So if you have 5 protons, that means your atomic number is 5, and you have a positive charge of +5 in the center, and then around the outside of the atom you have 5 electrons that are orbiting around. So that's going to make the total charge 0 because you have +5 and -5. So when we see this atomic number, and we want to figure out how many electrons are, that's how we're going to do that. Does that make sense to everyone? Because we know electrons are going to be what different atoms are sharing with each other and how they're interacting with each other. Yeah, so I got to the wrong. Yeah, atomic mass is the number of protons and neutrons total. Yeah. So if I give you a problem where I tell you there's 4 protons and 4 neutrons, you'll know the atomic mass is 8. So in this case with carbon has an atomic number of 6. That means there's 6 protons. Has an atomic mass of 12. So how many neutrons are there? Yeah. And how many electrons are there if the atomic number is 6? 6. Great. So that's how we'll figure out how many electrons, protons, and neutrons there are from those numbers. All right. So we're going to be talking about the octet rule. That's going to be a rule that we're going to be referencing a lot. So we talked a little bit about stability towards the beginning of the class. So atoms are considered stable when they're in a state where they're not going to be changing very much, where they're kind of relaxed, they're happy with the way they are. And atoms are happy with the way they are when their outer electron shell is totally filled. And that's going to follow the octet rule. So what the octet rule says is that in this first ring around an atom, in this first shell, we have 2 electrons. And then after that, each next shell fits 8 electrons, at least in the atoms that we'll be talking about. So that's where octet comes from, octet for 8. So initially we have 2 electrons, and then after that we have 8. And each shell after that is also 8. And so atoms are going to interact with each other and share or give away or take electrons to try to fill their outer shell, because that's going to make them happy and stable, and then they're going to interact with other atoms to try to make that happen. And that's going to describe a lot of bonding and chemical reactions that we're going to be talking about. So we have sulfur here. So what's the atomic mass of sulfur? 32. Great. So and what's the atomic number? 16. So how many protons are there? 16. And so we're going to assume that the charge is 0. So how many electrons are there? 16. Great. So in the first shell, we put 2. After that, we put 8. So now there's 10 electrons shown. So how many are going to be in the next shell, the next electron shell? 6. Great. So this is what that would look like. So there's 6 electrons in this outer shell. So is sulfur like really satisfied with the way it is, just floating around by itself? No. So it wants to get 2 more electrons, or give away 6, or share, so it gets to 8 on this outer shell. So it's going to go around kind of interacting with the rest of the atoms it bumps into, trying to make that happen. And as it tries to make that happen, it's going to be reacting and bonding, and it's going to tell you what other atoms are going to be near it and how they're going to be behaving. And as we build from that, we're going to see how big groups of atoms are behaving and how they maybe interact with water or interact with each other and form different bonds, and that's going to make up cells, and cells are going to make up people, and then people talk about atoms, so it's just like a big cycle. What's that? Yeah, so which one is 32 or 16? Which one do you think? Give a guess. What's the atomic number again? Yeah, but sorry, just for everyone. What's atomic number mean? No, sorry. What's the definition of atomic number? Maybe someone raised your hand. Sorry, someone want to raise your hand. What atomic number is? Great. So, and then atomic mass is protons and neutrons.
How do you know which one? Is it like protons are always going to be at the bottom?
Yeah, great. Good question. I should have mentioned that. So the atomic mass will always be on the top, and the atomic number will be on the bottom. But the atomic mass is going to have to be the bigger one. Good question, though. Sorry, so we're clicking 2 computers. Okay, so we talked about the octet rule and how atoms are going to want to try to interact with each other to get their outer shell to have 8 electrons. So that outer shell is so important that we give it its own number, its own name called the valence electron shell. So valence means outermost. So when we were talking about sulfur before, we said sulfur had 6 electrons in its outer shell. It'd have 6 valence electrons. So if we look at hydrogen, hydrogen has how many valence electrons? 1. Great. And how many more does it want? Just 1 more. Yeah, because the octet rule, you want 2 in the first shell and then 8 in the next shell. What about carbon? How many valence electrons does that have? 4. Great. Okay, I think we got this. So that, yeah, the outer shell, valence electron shell, and that's what's going to be important when we talk about bonding, because it's going to be those electrons that the atoms are either going to be trying to get or give away. Okay, so now we're going to talk about bonding. So bonding is going to be the force that's going to keep atoms near each other. It's like a glue between 2 different atoms. And so we're going to be able to describe bonding by looking at the octet rule, but the types of bonds, there's different strategies on how to fulfill the octet rule. So when we talk about molecules, that's going to be 2 atoms or more that are bonded together. So a molecule is just 2 or more atoms that are stuck together, and now they float around like one particle most of the time. So this is going to happen because the molecule is a more kind of stable configuration for the atoms, and the atoms want to be stable because things that are stable are going to stick around longer. And when we look into chemistry, we're going to see the things that did stick around longer. So generally, when we see atoms, they're going to be in the configuration that makes them the most stable. Does that make sense? It's kind of I feel like it gets more clear and then confusing in like waves, that concept. So things we see are going to be in the most stable configuration because that's what sticks around the longest. Maybe this is overkill, but
because if they're missing an electron, they're trying to suck one from somewhere else.
yeah, and when we look at them, we'll usually see them not doing that because they already, yeah. Great. So they're going to be trying to fulfill this octet rule, and the way they can do that is through either ionic or covalent bonding. So these are the 2 main types of bonding that we'll be talking about. So ionic bonding is where one atom either gives or takes an electron to another one. And then since they have an opposite charge, because one is now positively charged and one is negatively charged, now they're going to stick together, just like 2 magnets if you had like a north and a south pole. So ionic bonding, one of the atoms is going to give an electron to the other. And now they're going to stick together because they have an opposite charge. So maybe one had 1 too many valence electrons and one had 1 too few. And so now they just gave one to the other, and now they're both happy with the octet rule. They're both stable, but now they're going to stick together because they're oppositely charged. So covalent bonding is a little bit different. Covalent bonding is they're going to be sharing an electron. So the electron is kind of going to be orbiting both atoms, and it's going to make them stay really close to each other so that an electron can get around both of them. So those are the 2 types of bonding. One is giving and taking, and one is sharing.
Hold on.
Yeah, okay.
Yeah, do you not want us to write this down?
I mean, it's already all online, so you don't have to write it down. But if writing it down helps you learn, then I can slow down so you have time to write it down.
Yeah,
Okay, that's...
because it takes me like 3 times. So I write it, I look at it again, and then I look at it.
All right, well, I will try to go at a speed that makes that possible. Oh, wow, it is getting close to 7. All right, that's okay. We'll get as far as we get, but we'll make sure that we cover everything adequately. Okay. Okay, so chlorine has 17 electrons, so how many are in its valence shell? 7. Great. So we had, I made so many mistakes in this slide. This should be just 2 on the inside, not 4. And then 8 here, and so that puts 7 on the outside. Oh, thank you. That's got to count for something. Sodium, how many valence electrons does sodium have? Just 1. So what do you think is going to happen when we put these 2 things near each other? Yeah, chlorine's gonna steal sodium's electron. What a jerk move. And so when they do that, Now sodium has one fewer electron than it had before, so now it has a positive charge because we took away a negative, and now chlorine has a negative charge. So it had 7 before, and sodium had 1. So I had this like clever little animation. So now it has 8, and sodium has 0. So now it does because it took an electron from sodium. Yeah.
Sodium has it because it no longer has that outside valence shell.
Exactly. Great. Yeah. So sodium had 1 on the outside, just kind of hanging around, not where sodium wanted it to be, and so sodium gave it to chlorine, and now it's now there's a difference in charge.
So are you saying if it doesn't have a valence shell, it's positive?
No, not necessarily. So the reason that sodium is positive is because it has 11 protons, and it had 11 electrons, but it lost 1. So it still has 11 protons, but 10 electrons. So there's a difference of 1, so positive 1, so that's a positive 1 charge.
Okay.
I can write that down if I can find a marker.
So my question is, does it really have a valence shell? Empty valence shell with no electrons?
Well, no. I mean, it doesn't have an empty valence shell. It just means this is now the valence shell, and now it has 8 in its valence shell. Yes. So sodium originally had or has 11 protons, and now it lost an electron to chlorine, so now it only has 10 electrons. And so these are positive and these are negative. So since it lost an electron, now it has a charge of positive 1. Is that, yeah. And now, so since negative charges are going to attract, now sodium and chlorine are going to float around together because they're attracted to each other because of the difference in charge. And that's the basis between the ionic bond. It's called ionic bond because these are now ions since they're charged.
So the atomic mass 21? Sorry.
No. So the atomic mass of sodium, so the atomic mass is the number of neutrons and protons, which didn't change. So it's still 22, I think, right? Yeah.
And you said it's
So-
called ionic because they have a charge?
Yeah. So an ion is a charged atom, either positively or negatively. So an ionic bond is a bond between charged atoms. Yeah. All of these transitions seemed like a better idea when I was making the presentation. Okay, so like I said before, the difference in charge is because sodium lost an electron, so it kind of donated that electron. We call that the electron donor. Chlorine, I would have called it the electron stealer, but electron acceptor is the term that we use. So it's the electron acceptor. So that's how we're going to describe ionic bonds, is we have one that accepts the electron and one that donates the electron. So, like we said before, in addition to the ionic bond, there's the covalent bond, and that's where we're going to be sharing electrons between 2 different atoms. So, if we look at oxygen, so oxygen had 6 electrons in its valence shell, and so it's going to share enough electrons between 2 different atoms so that each of these has 8 in their valence shell. And they're just going to kind of go between both of them like that. So another example, carbon and hydrogen. So we have a carbon here. Carbon had 4 electrons in its valence shell, and hydrogen only had 1. So carbon's going to get surrounded by 4 hydrogens, and they're all going to share 2 electrons between the 2 of them like this. So now hydrogen has 2 and carbon has 8. So they both didn't they didn't change any of their charges because they didn't kind of give or take electrons, and they're just sharing them. So they all still are neutrally charged, but they're all sharing electrons. Does that make sense? This one's like a little harder to grasp in my opinion.
So the hydrogen has 2 and it's sharing 1 with the
Yeah.
and the carbon.
So the hydrogen initially only had, maybe I will write it. So hydrogen had 1, and carbon had 4. Can you guys read? Can you read that, or is it okay? And so what happened is now each hydrogen, and so the carbon is surrounded by 4 hydrogens. Each hydrogen is going to share one of its electrons, or its 1 electron, with the carbon. So now carbon kind of has 8 because it's getting the 1 from the hydrogen. And then the carbon is going to share 1 electron with each hydrogen. So now hydrogen kind of has 2 because it's getting 1 from the carbon. Yeah, I know. It does get, because it's like where is it then? Where is the, that's, so the thing, oh no, the thing about electrons is they're not really discrete little particles like this, the way we make them look. It's not just like 1 particle that floats around. They're actually kind of like smeared around the entire atom, and now they're just like smeared a little closer to the carbon, enough to satisfy carbon's octet rule. It doesn't really have all of it the way it would normally, but it's enough that it's stable. Does that help, or is that still? There's a figure coming up that I think might help you, and if you're still confused, then so what really happens is these electrons are kind of spread between each other like this. So hydrogen and oxygen can share an electron like this, where oxygen is taking more of the electron than hydrogen is, and it leaves the hydrogen a little positively charged because it has less of the electron, and the oxygen is a little more negatively charged. And so both atoms will fulfill their octet rule in a covalent bond, but one can be slightly positively charged and one be slightly negatively charged. And where the electron is going to be determined by what we call the electronegativity. The electronegativity is like how much a certain atom is going to pull on the electron. So oxygen is kind of a bully. It's like a lot stronger and a lot more electronegative than the hydrogen. And so it's going to take more of the electron from it and leave the hydrogen a little positively charged, and the oxygen will be a little negatively charged. How's that concept? This one's always a little bit tricky, but I feel like if we think about this diagram, we can kind of see that electrons are kind of shared unequally sometimes, and a certain atom will get more of it, and the one that gets more of it we say is more electronegative. So it pulls more strongly on the negative electron. Any questions about that so far? All right. So
Carbon will have more electronegativity than hydrogen.
they're actually pretty close. So there will be another figure where we look at the periodic table and which ones are more electronegative than others, which atoms, and it's not as obvious of a rule as it would kind of seem initially. It's not always the bigger one. It's also like how badly does it need just like 1 more electron, or how badly does it want to give away 1 more electron? Kind of matters too. So what determines whether or not bonds are going to be polar or covalent or ionic, and if they're covalent, whether or not they'll be polar or non-polar, is going to be the difference in electronegativity between 2 atoms. So if 2 atoms are bonding that are equally electronegative, they're going to share the electrons equally because they're equally strong, and so it's like a tug-of-war team where both teams are like the same strength. It's going to be an equal sharing of this electron, and so there's going to be like no difference in charge anywhere because they're going to share it between the 2 of them. A polar covalent bond is where one atom is much more electronegative than the other, and it's going to pull more strongly on the electron and have more of it. Ionic bonds happen when there's a really big difference in electronegativity. So like sodium and chlorine have a very large difference in electronegativity, and that's why one just gives its electron away. Because one really wants an electron, so it's really going to pull on it, and sodium really didn't want an electron. It wanted to get rid of it, so it has a very low electronegativity.
Oh, that makes sense.
Great. Good. So polar and non-polar, this is a description of how equal the sharing is. So if the sharing is really equal, like between 2 oxygen atoms, like a molecule of 2 oxygen atoms, they're going to have the exact same electronegativity. So the sharing is going to be totally even, and that's going to be a nonpolar covalent bond. Oxygen and hydrogen, like we saw before, that is not an equal sharing. That's a polar covalent bond. So 2 types of bonds, ionic and covalent, and then within covalent bonds, there's polar and nonpolar. But it's kind of like a spectrum like this, really. Okay, so oxygen and hydrogen. So we have oxygen here. This is an electronegativity. You don't have to memorize any of this. This is just kind of like an illustration. Oxygen has an electronegativity of 3.5, which is very high, and hydrogen is 2.1. So 3.5 in this scale is substantially higher than 2.1. So oxygen is going to take a lot more of the electron, and hydrogen is going to take less of it. So that's going to leave the hydrogens with a partial positive charge and the oxygen with a partial negative charge. So water is really important in biology. So biology is always surrounded or in a solution of water. And so the fact that water is very polar like this is going to be important to us moving on. Okay, so I wanted to do a review after this, but I think we're going to have to do that when we start class tomorrow, because it's 7 now. Yeah, you're right, Thursday, sorry. Do not have class tomorrow. But before you go, here's an overview of bonding that can help you summarize the lecture. 2 types of bonds, ionic and covalent, and within covalent bonds there's polar and nonpolar, and that's determined by the difference in electronegativity. All right, so that was class for today. I'm going to try to upload these PowerPoint slides with my audio on them to Sakai, so hopefully that works. And so I'll see you guys all on Thursday. Unless you have lab today, if you're section 130, then you have lab at 7:05, just around the corner. Great, thank you. Are you 131? Yeah, so you'll be Thursday, not tomorrow.